Hi. In this lesson, we need to have a look at the texture of igneous rocks. So how the crystals within an igneous rock tell us about how that rock cooled. Now you might be wondering why I'm starting this video with an image of a quarry. This is a very, very famous quarry. It's in the English Lake District. It's a place called Shap. And this quarry is digging out one of the most famous decorative stones that's used across the UK and beyond. There are examples of this we can find, for example, on the plinths of statues in Cardiff city centre. This rock gives us an interesting story, perhaps, about how it formed. But let's see how we go working it out as we work our way through the lesson. We're working on pages 5 and 6 of our Theme 5 booklets. Let's go. So we have these two igneous rocks, rock S and rock Y, that were described in the last lesson that we were working on. And you should by now have completed the questions on page 5. If you haven't done that, pause the video and have a go at those questions now. If you have completed those, let's see what we've come up with. Let's deal with these rocks one at a time. So we'll start with the questions that relate to rock S. Now this type of rock, or the texture of this type of rock, so the arrangement of the crystals within it, is described as being porphyritic. Now this is a word that we use in geology to describe what's going on within this rock. We'll come back to its meaning in a moment. So question A1, I asked what type of magma rock S would have formed from, and it's silicic. The way we know that is that the minerals within rock S include quartz and orthoclase feldspar. They're silicic minerals. We find those minerals in abundance in silicic rocks. If we jump onto question C then, if we describe the texture of these crystals and their relationship with each other, what we see are these large rectangular shaped crystals of feldspar. Some of them, as we measured, up to maybe 30 millimeters across. And then they're surrounded by smaller crystals of other minerals, the quartz, the plagioclase feldspar, the mica that's in there. So we see these two very different sizes of crystals. Now, if we bear in mind what we've learned before about the relationship between size of crystals and the rate at which they cool, the fact we've got two lots of crystals here tells us we must have two stages of cooling. An initial slow stage to make those large orthoclase feldspar crystals, and then a faster stage later on that's crystallized all the rest of the magma around it. And it's that that's key to a porphyritic texture. We describe these larger crystals as phenocrysts, and we describe the smaller crystals as ground mass. Finally then, if we name this rock, this is a granite. It's a very well-known type that we call a Shap granite because of the location it comes from. But it's a very beautiful rock, particularly when it's cut and polished. Anyway, if we now look at rock Y we describe as being equicrystalline. We'll come back to that in a moment. So the magma in this case is mafic, And the reason we know that from the minerals that are in it, we've got augite in there and we've got olivine. Those two minerals are mafic minerals. Question D, then, we ask you to describe the texture of this rock. And what we see here are smaller crystals of all types. They're probably less than a millimetre across these. And the crystals are all a similar size. It's that makes this rock equicrystalline. As the name would suggest, equal crystals. The way this forms, then, we know there are small crystals, so therefore it must have cooled quite quickly, but it cooled at a constant rate. That's why all the crystals are the same size. And finally, the name of this rock, this is of course a basalt. So, this is the Shap granite, rock S. This is a classic example of a porphyritic texture. We have the large feldspars, as I said, which we call phenocrysts, and the finer grain crystals around that are the ground mass. What I'd like you to do is to have a go at the questions based on this is a diagram of a rock just like the Shap granite, and I'd like you to have a go at the questions on page 6. So that's question 4 of your booklets. Have a go as well at the digging deeper activity. How does this relate perhaps to the risk from volcanic eruptions? Something else to think about as well is this rock. This is a rock from the Land's End granite down in Cornwall. How do you think this particular rock cooled? What's the story behind this? Why is this rock particularly special? Anyway, have a think about that. Press pause and have a good look at the rocket in this photograph. We'll talk about it in the next lesson. So, as we watch the sunset of the Shap Fells in the lakes, we can see that texture of igneous rock depends on the rate of cooling. And we as geologists can interpret that texture from careful observations of the crystals and their relative sizes within the rocks. It is important, though, that we are familiar with the language that's used, with that terminology. We do need to think about where we actually go about finding these igneous rocks, where they form, as well as how they form, but that's for another lesson. I'll see you then.